So we will do this first, hopefully quickly, so we can get to the other stuff. And the other stuff that's coming that you see in the handout in front of you has some really interesting thinking that we did a little bit of it in trigonometry, but not much. This is where we really get into it, and I think it's really important. It's going to be really useful for all the graphing that we're going to do. So like today is kind of an important day to make connections and really understand what's going on, building foundations so that you can do the graphing that's coming. It's quite intense graphing coming up. So how do we simplify rational expressions? I don't think you need to write this down. You can just watch. I'm going to do a demonstration quickly with some questions with numbers. Okay, so say I was doing these things. So this is just reducing a fraction. And this is probably not the way that you would think about it or the way that you've done it before, but I can break 8 up into 2 times 4, and I can break 6 up into 2 times 3, and then I can see the factor in both of them, and they divide to 1, so they're gone. You would probably do this question, and rightly so, by dividing both the top and bottom by the same number, which is essentially the same thing, right? But this way of seeing it is more helpful for rational expressions. And it is reminding us that like factoring a number, factoring a rational expression, all that stuff is all kind of the same thing. And we have to have things broken down into their factors in order to see what will cancel or divide out. And then for this one, how am I going to add these fractions? Well, I need a common denominator. So what am I going to do here? I need a bit more room. I'm looking for something that's common between 2 and 3, common multiple of them, which is 6. And so to turn these into 6, I have to multiply the 2 by 3, but whatever I do to the bottom, I have to do the same to the top. And again, we saw a lot of this, in the trigonometry units, where like we conveniently multiply by 1. So we're not changing anything, we're just multiplying by 1. And I do the same thing. Whoops, I did that wrong though, didn't I? And I do the same thing over here, but in this case, multiply by 1 as 2 over 2. And then I get 3 over 6, which you can see is the same as a half, because we can't change these expressions, plus 4 over 6, and then I just add the tops. And if you make mistakes in those places, when we come back to this down the road, like if you add fractions wrong by not getting a common denominator, or if you add the bottoms as well and you said this was 7 over 12, like that's going to cause a lot of issues. So those are not the mistakes you want to make. Right? So you want to really make sure that you've got the fraction stuff down. Now, I hope that makes sense. How does that apply to rational expressions? Well, in order to simplify A, because there's no operation, there's no multiplying or adding or anything to do, so it's just simplifying, what are we going to do?
Take out x plus 6.
Yeah, so, but we'll factor it first so you can clearly see it. I'm sure you could do that in your head. But x squared minus 36 factors into x plus 6, x minus 6. And then those reduce. And this is x equals x minus 6. And what are we missing here? What was I going to say? It's interesting when you do this in grade 11, you kind of don't have any context for it, like why you would do that. And I think a mistake a lot of people make, which again is coming up more in B and C, is when do you factor, when do you expand, when do I have to, when do I not? And hopefully there will be more clarity this year when you're actually using these skills to do something about why you would want to factor or not factor in certain cases. And like grade 11 starts off pretty strong, right? Because you do this whole unit on rational expressions. There's a ton of factoring in it. It's pretty heavy on the algebra, way more than anything you saw in grade 10. It's at the very beginning of the class, first 2 weeks of the course. Kind of hits you like a truck, right? And but it's good algebra, it's good stuff. But now we'll get to see sort of what the point of it, because you didn't really use any of those skills in grade 11. So we will eventually get to see why we get to do that. And hopefully that'll help with some of those common grade 11 mistakes. So what am I missing here? Well, I kind of have an answer. Restrictions. What's my restriction? Anybody know, Max? So x cannot equal -6. Why?
X plus 6 is the denominator.
Yeah. Good. And why is it a problem for a denominator to be 0? Because you can't divide by 0. That's right. It's undefined. But so what? Who cares? Why do we write restrictions? Why does that matter? Like what? My point is, what even is all of this? So we simplified it. Like I did a bunch of steps and I followed some rules, but who? So what?
Is it only like half of another function?
Interesting. What do you mean by that?
I remember like we had like a parabola and then there was a sideways parabola.
That's restricting the domain, so that's a different thing. But what you said is interesting, and it's on the right track. Isaac, you had your hand up. What were you going to say?
When do you restrict it? Like, why is it 6 as a restriction?
Because we never divided by x minus 6. It's only when you're dividing by a factor that will mean you're dividing by 0 is when you count those as restrictions. Anybody have any idea? So again, go ahead. Yeah, you're on the right track. It won't, that's true. But this will. What even does all this mean? Why what is the point of this? What would the graph of that look like? It's got a parabola on top. Do you think it would look like a parabola? Because it actually doesn't. I mean, think about what this means. What do you think? No, it doesn't look like that. Reciprocal graphs do look like that. We're going to look at those later, but it looks like that. It's that line, y equals x minus 6. It's a straight line. That's what that graph would look like. Like, that's what this means. If this expression equals this, what does that mean? It means their graphs would be the same. They would be the same function, right? That's what it means for two expressions to be equal to each other. They would have equal values. For all values of x, they would equate to the same thing. So if I put 5 into both of these, I would get the same thing. If I put 10 into both of these, I would get the same thing. If I put -6 into both of them, I don't get the same thing, do I? Because -6 minus 6 is -12. But if I put -6 into there, I divide by 0 and it's undefined. So what we're saying is these two expressions are equal in every single way, meaning the graph of that would look like that, except for at that one position, where it wouldn't look like that. What would it look like? Well, that's what we're going to get into in the first half of this unit. It's not an asymptote if some people are thinking that, but it's something sort of similar in some ways, but it's a bit different. Anyway, let's do the next one. This printed out funny, so I got to fix this. This is supposed to be a 25. It's probably right on your page. Yeah. This one over here is supposed to be a 12, I believe. Okay, so how do I divide fractions?
Should we factor it first?
Yeah, possibly. Does it matter? How do we divide fractions?
Flip them upside into reciprocal.
Yeah, flip and multiply, or multiply by the reciprocal. That's right. So if I flip it first, or factor it first, won't matter. But sure, let's factor it first. We are going to flip and multiply, but we want to factor everything first. Is that missing something there too? It's 28. Thank you. Yeah. This weird glitch in the way that it prints some documents. It just drops a character every once in a while. It's so bizarre. Okay, so factoring the top. I'm going to try to do this quickly. Maybe you already beat me to it, but divided by, and if you were doing this, you could probably do it all in one step. Plus 4 x minus 2 over, and this is x plus 5 all squared, right? Okay, so now I'm going to flip and multiply. And in this case, why do we want it factored? Well, because I can see the different parts that will divide to 1, that will cancel. And remember, this is all multiplication. If I was adding these two fractions, I couldn't do this. But because I'm multiplying, I can go like this and like this, right? Okay. So then I multiply the tops. And the bottom is just x minus 2. And then what do we need? Restrictions. So what can x not be? Abdul? Okay. Why 7? Did we ever divide by x minus 7? I think 7's fine because it's never in a denominator. You have to look for all the denominators throughout the entire question. So I divided by x plus 5. I divided by these two here. And I divided by x plus 5 squared again there. So wherever something is in a denominator, so I think it should be negative 5, negative 4. And then you're right, positive 2, but positive 2 is a strange one for me. And again, this is something that's kind of interesting that I think in grade 11 you would just do it because that's what you're sort of told to do. But I'm not sure I understand why we need to have 2 as a restriction here. What do you think? Why would I feel that way? Yeah, like this function, whatever that mess is up there, is the same as that at 2 in that they're both undefined. So to me, a restriction is like, because I divided these away, the x plus 4s and the x plus 5s, maybe I divided that one on the bottom away, and it's not in what's left, you need to restrict them. Because I can sub negative 5 into this, and it's fine. But where I came from, I can't. So it's fine to, don't get me wrong, it's fine to put 2 as a restriction. It doesn't really matter. It's just interesting to me when you think about the actual purpose of a restriction, why we don't need that. It's in there. It's like this is naturally has that restriction in it. Try to divide by when it's 2, right? And it won't work. Okay, last one. So what do we do when we are adding fractions? We need a common denominator. Oh, and sorry, going back to this one. Is there any reason to expand? This is what some people struggle with in grade 11. Is there any reason to expand and simplify this? No, I don't see why you would. So you leave that alone. Again, when we get further into this next week, hopefully that'll be more obvious. But so I have to factor both of these first. And to get a common denominator, you have to have all the same denominator for both. They already have x plus 3 in common, so all I have to do is, I'm thinking like add what's missing. So this has x plus 3, x plus 1, but it's missing x plus 4. So again, I have to multiply by 1. So I multiply by x plus 4 over x plus 4. And this one has x plus 3 and x plus 4, but it's missing x plus 1, so I have to multiply by x plus 1 over x plus 1. So 2 times x plus 4 over x plus 3, x plus 1, x plus 4, and 1 times x plus 1. Like that. And now what do I do? Remember we said this before? Just add the tops. So this is 2x plus 4 plus 1x plus 1, which is just x plus 1, over that whole mess on the bottom. And what about in this case? Should I expand and simplify? Yes, I should. Very good. Why? Well, we'll see in a minute. 2x plus 8 plus x plus 1 I'm sure you could save a lot of steps if you were actually doing this. We're doing extra steps here. So 2x plus x is 3x, 8 plus 1 is 9. And what do I have to do now? Refactor. And this is, like I say, the part that in grade 11 a lot of people have a problem with. Well, we already factored. Why are we expanding? Why are we refactoring now? Like, I don't understand. But it's because, look, we can simplify this even further. So this actually equals 3 over x plus 1, x plus 4, as long as x doesn't equal -3. And then -1 and -4 are restrictions you might add as well because they're in there, but like I say, you don't really need them, I don't think. Oh. So this is actually something that we are going to learn a little bit about how to graph it today. Not quite with the 3 on top. We're not really interested in doing that. But if it was a 1 on top, we could definitely graph this today. This would be a lot harder to factor. Or why do I keep saying factor? To graph. Or even any of these other things would be a lot harder to graph. It's easier when I've simplified it. That's one reason why we simplify. As you know, it's just easier to work with something that's more simple. Okay, so that is, all of that was only extra stuff that you can think about. Like I said, there was a review posted to the classroom that you can do optionally, maybe a couple of questions a day. It's not that much and it's not that hard. I don't think the questions are even as hard as those ones that we did. But if you want a little bit of practice to make sure that you're ready before next week. So this is what we're actually doing today, which is graphing reciprocal functions. And as I said, yes, you did this sort of last year, but you only did one type, and we're doing it in a very different way. And notice that I added from your handout part 3 here. I don't know if you have to write all that down, but we're going to do it at least for the first couple because it's in the homework. So we're going to consider each pair of functions and complete the following. We're going to graph them, but we're going to graph f first, f at x, and we're going to use it to figure out what we can understand about G. We're going to use F to figure out what G is like. Okay? We're not graphing with transformations. That won't help. You could graph this one with transformations. It would be easy, but the other ones that are on the back of your page that are coming up next, you wouldn't be able to graph with transformations. And we're more interested in this thinking that goes along with thinking about what F can tell us about G. As I said, this is really, to me, important for what's coming up, especially in the first half of this unit. It's kind of a big thing. Okay. And in other words, G at x is equal to 1 over f at x, right? That's why they're the reciprocal of each other. And what is f at x? What is that graph? Now, folks, graphing lines, straight lines, is something you really should know, and you really should be good at it. It should be quick. I'm not really reteaching it, but you can ask questions if you have any, but like it's going to pop up here and there in this course, and if you're taking calculus there too. And if you don't know how to graph a line, you're going to be like getting stuck a whole bunch of times. So make sure you know how to graph a line from grade 9. And so this line has a y-intercept of -2, an x-intercept of +2, and a slope of 1, right? Slope and y-intercept is just how we would do this. So I go down to 2, find both my intercepts. And graph. It's kind of hard to graph on a computer. I'm going to try that again, actually, but. So that's F. Now, how do we use F to discover things about G? Well, they're the reciprocal. And then there's I think 4 or 5 sort of key areas that you need to think about and look at whenever you graph. So we're going to do these one at a time. The first one we'll look at is 1. I think I need to redraw this again because, okay. Hopefully that's better. What is the reciprocal of 1? It's 1. So when f is equal to 1, g, its reciprocal, will be equal to 1. So you should always think about 1, and the graph, a graph and its reciprocal should always cross each other at 1. What is the reciprocal of -1? -1. So the graphs will also cross at -1. So those are like anchor points that you can always find after I've graphed the original function. I look for where it's 1 and -1, and I know that my two graphs will meet. And a lot of people forget that when the quiz or a test pops up, just so you know. So you try to remember that. What's the reciprocal of 0? Undefined, it's not 0, right? It's undefined. You can't divide by 0. So 0 over 1 would be 1 over 0, which is undefined. What does undefined look like on a graph?
You said it wasn't. I think it's like an asymptote.
Yeah, it's an asymptote. I didn't say it wasn't. Something else is like an asymptote. That's something else. In this case, it is an asymptote. So we're going to draw that in. So these reciprocal functions will always have asymptotes where the original function is equal to 0. Because when I do 1 over that, 1 over 0, I get undefined. So look what we've done. We graphed the original graph. We found 1 and -1, and we found 0. We're starting to get a sense of what this graph will be like, sort of. Not much yet. Do you remember what the reciprocal graph looks like? Vaguely? But here's the next part that's different. Do you have a question? Here's the next part that's different. And again, it's very, very important. And very new kind of thinking that we haven't really done yet. But because it's all thinking about reciprocals. When this graph, f, is going this direction, and it's getting really close to 0. So I'm imagining myself on f coming down, and f, the y values of f are getting smaller and smaller and smaller and smaller and smaller, right? So I'm coming down here. What will the reciprocal be doing? What's the reciprocal of a very small number? So imagine yourself coming down this line, getting closer and closer to 0. 0.1, 0.01, 0.0001. Okay, you're getting closer and closer to 0. You're getting smaller. What's the reciprocal of those numbers going to do? It's going to get bigger. What's 1 over 0.1? What's 1 over 0.01? 100? 1, right? So 1 over a small number is a big number. So as f is getting smaller and smaller and smaller, and we know g starts here at 0, it's getting bigger and bigger and bigger, approaching that asymptote going up. Now, as f gets really, really, really big, what does its reciprocal do? Gets really, really, really small. So as f is getting really big, g is getting really small, and that's why it approaches that asymptote there. But it'll never reach 0, will it? Because this goes off to infinity, but it'll always be some number, like a billion. 1 over a billion is really small, but it's not 0. So you'll never take the reciprocal of a number and get 0. So this one goes something like this. And by the way, you could find other points. Like I could go to 2 and take the reciprocal of 2, and I could go to 3, and I didn't graph very well, I kind of missed there, and take the reciprocal of 3, but that's not really what we're doing. We're thinking about the behavior of the graphs. Should look like that. Always try to draw graphs. I know this seems kind of obvious and maybe it seems like a strange statement, but don't make the graphs, don't add any properties to them. Don't make them do anything weird. In grade 10, what some people do with parabolas, and you know very well what a parabola should look like now. It looks kind of like that. People draw them like this and have the arrows coming back in like that. Or people draw them like this for some reason. Like when they finish, they point out. They probably draw it twice. They probably go, for some reason, they have them start like turning to go out. They don't do that. Don't add those kinds of properties to any shape as much as you can. So you have to kind of get familiar with what these graphs look like so that you don't do anything weird. And then what happens here? As f gets really, really small, closer to 0 and negative, what will its reciprocal do? Get really, really big and negative. And then as f gets really, really, really big and is still negative, what will its reciprocal do? It'll be smaller and negative. So this one's going to go like this and like this. Like one thing that you would always want to be careful of is you don't cross asymptotes, usually. If you're crossing an asymptote, it's for a reason. You will see that down the road. Otherwise, make sure your lines, when you graph them, don't cross the asymptote. Okay? So that was a lot of work for something that would have been easy by the grade 11 version, but that's how we are doing graphing. We graph this function, x minus 2 in this case, graph it first, look for 1, -1, 0, and then think about, well, this graph's getting really big, so what will the reciprocal be doing? Getting smaller. Now, at this point, it's getting really smaller, so what's the reciprocal doing? Getting bigger. Okay, and then we are supposed to do this, state the asymptotes. So this has a vertical asymptote at x equals 2. It has a horizontal asymptote at y equals 0. Domain range, you know how to do that. Although for one of the graphs that's coming up next, it's a little bit interesting. So the domain for this one, x is an element of the real numbers such that, what is it? Do you remember from grade 11? How you do these? Want to try? Yeah, x does not equal 2, right, where the asymptote is. So it'll be everything except 2. Range, same thing, except y cannot equal 0. What else does it say? Intervals of increase and decrease. Do you remember this? We've done this already, so I'm not going to re-explain all of it, but we've already done this. And intervals of increase and decrease is, as I go from left to right on the graph, what are the y values getting bigger or smaller? If they're getting bigger, you're in an interval of increase. If you're getting smaller, you're in an interval of decrease. So what's happening? I'm going to start at the very left of the graph. Are the y values getting bigger or smaller here? Smaller. And then we skip over the asymptote, and I start back up here, and what are the y values doing here? Still getting smaller. So does this graph ever have an interval of increase? This one doesn't. Yeah. So, whoops. So intervals of increase, none. And decrease, we're going to write it with intervals. So x less than or equal to 2. And then x greater than or, no, not equal to, sorry, whoa. Greater than 2. That's why we had to do it, because we had to skip over 2. Everybody okay with that? And finally, this part's new. It's pretty easy. But it's new. Positive and negative intervals, and the reason why we're doing it is it's important for what we're doing in the second half of this unit. Positive and negative intervals is just literally where the graph is positive above the x-axis and where it's negative below the x-axis. So where is this one negative? Let's start with negative, I guess. All the way up to the asymptote, it's always below the x-axis there. So when x is less than 2, and where is it positive? Everywhere after the asymptote. Not equal to 2, the graph doesn't exist at 2. Ready to try another one? Let's do it. On the back, something that's very different. This is not something you would have sketched in grade 11? So we're going to start with F. Now F is actually already in graphing notation like vertex form, right? It's already in a good form to graph. It's just got a vertical shift down 4. That's it. Do you recognize that? Again, graphing parabolas, we've done some of this already, like in the polynomials unit, so hopefully you're going to be okay with that. But graphing a parabola is something that you should be good at and be able to do quickly. It's not really, we're not relearning this part. But one thing that can be useful to do, in some cases you might have to, you might not, but you're going to see as we do this, that it could be useful to have it in factored form. So I'm going to factor it as well. Why? Because factoring gives us the intercepts, and the x-intercepts are where we have asymptotes, right? So it's kind of an important part of the graph. So this has a shift down 4 and no stretch or compression, so otherwise it has the same normal shape of a parabola like that. And there you see the intercepts of 2 and negative 2. And how do we graph g at x? We look for 1 and negative 1. So I see 1 here, and negative 1 here, and here. We look at the zeros, and that's where asymptotes are, vertical asymptotes. And then we use this kind of thinking. So I'll start here with this part of F. Okay, as I come down on this graph and get closer and closer to 0, G is going to get bigger and bigger and bigger. As I go up this direction on this graph, G is going to get smaller and smaller and smaller. So it's going to go like this, something like that. Now this is what people do on the quiz or the test. They just kind of go like this. But we know they have to cross at 1, so that's not good enough. So you've got to come down here. Whoa. And have them actually cross at 1. And it's going to do the same thing on the other side. F is getting really big, so G is getting really small. F is getting really small, close to 0 when it passes through the x-intercept, so its reciprocal is going to get really big. You never, ever, ever cross. This is actually a rule. You never cross a vertical asymptote. It's not possible. Okay? So that line can never cross the vertical asymptote. And don't forget, some people just get used to the shapes, and again, they kind of think every graph looks like this one, and they just draw it the same way, but they don't think about the little details. But remember, this is reciprocal. Whoops. So what's the value there? Negative 4. What's the reciprocal of negative 4? Yeah, negative 1 over 4. So we've got another point, and this is actually an important one. We've got another point there. And it's getting really close to 0 here. It's at negative 1/4 there. It crosses there, and so this one gets really big. And negative 1/4 crosses and then gets really big, but negative. And people just think every graph from now on looks like this, so they go whoop, whoop, whoop. And it's like, no, that's not really the way these look. Like, there are minor details to these shapes that you have to think of. 1 and negative 1, your asymptotes. And then exactly what this behavior is like, and points like this one right here, which is the reciprocal of your vertex. You have to think of that. Well, your vertex is at -4. The y value is -4.
Oh,
So the reciprocal is -1/4, right? Okay, now we have to do all of this other fun stuff, and it started with the asymptotes. So in this case, we have two vertical asymptotes, and they're at x equals -2 and x equals +2. And we have one horizontal asymptote at y equals 0. My domain is pretty straightforward. Does anybody want to try the domain? Abdul? What about them?
X cannot be.
Yeah, so x not equal to ±2, but it exists everywhere else. Now the range is a little bit different. Anybody want to try the range? Let me think of why it's a bit different. So greater than 0 sounds good to me, and not equal to, right? Because that's an asymptote. But it's not actually less. It's not x is less than 0. What is it? Nice. X is less than -1/4, right? Make sure you understand this. The graph never goes above that point, so there's a gap between 0 and that point. So it's actually x less than or equal to, because it touches that point, -1/4. Interval of increase. So from here it's increasing. It's getting bigger. Doesn't exist at the asymptote. Starts low and gets bigger again until that point. So this is all increasing and increasing, and then decreasing and decreasing. Yes?
For the range, you have to write the y.
Oh, y, thank you. Yikes. Yeah. Okay, so for interval of increase, we've got x less than 2 and -2. -2 less than x less than or equal, or doesn't matter if you include that point, but 0. And then decrease, it's decreasing in the second part of the graph. So from 0, less than x less than 2, and x greater than 2. And where is it positive? It's just where it's above the x-axis, so it's positive here at less than 2 and greater than 2, and it's negative between -2 and 2. So I'll write that out. So it's positive when x is less than -2 and x is greater than 2, and it's negative from -2 less than x less than 2. Any questions about that? All right, let's move on. We got a couple more. We're going to be a bit quicker. We won't do all the details of these last two. To graph f, we have to graph f first. What do we have to do before we can graph it? Factor it is a good idea. There is something else we might want to do to it. So I know I'll have x-intercepts at -5 and, whoops, I'm going to do this one in red again. -5 and -1. What else maybe would you want to do?
Wait, why are they? Oh,
From grade 10, how do you graph a parabola? Transformations, but it's not in the right form for that, so what do we have to do? Huh? Complete the square. Thank you very much. Again, I'm not teaching this, but this is something you just want to do. It's the important skills from grade 10 that you haven't done as much of since then. We haven't really done it, but it pops up once in a while for us. So how do you do that again? I will go over this quickly, and if you have other questions, you can ask. So I separate the x squared in the x term. And what do I do inside the brackets? Yep. Not 5 though. Not 4.
3.
Not 3. There you go, plus 9 minus 9. So that's what makes this a perfect square trinomial. In other words, half of the x coefficient, half of 6 squared. So you take 6 divided by 2, you get 3 squared to get 9. And you add it and subtract it. Everybody had that part down. That's good. So you're effectively adding 0. And then if you had a number out front, you'd have to multiply. But that might happen. Pull the negative 1 out. And then simplify. This is x plus 3 all squared minus 4. So now I have it in vertex form, and I can graph it. So it's got a shift to the left 3 and down 4. And if you were careful, you probably could have found the vertex from the intercepts. There are other ways of graphing parabolas than vertex form. So you don't necessarily have to do that, but you have to get the right graph for the parabola. Okay, and then graph it. Oh, and I'll include these 2 points because I know where they are, so we might as well. So we get a nice looking parabola. Then what are all the things that we have to look for and find? The asymptotes, which will occur at the x-intercepts of this. One and negative 1, and then think about the behavior. And you can just watch if you want. I can see that f is getting small when I'm coming way down here, right? F is getting smaller, so g is going to get bigger. And they pass through each other at 1. And then f gets really, really big, so g, its reciprocal, is going to get really, really small. Same thing on the other side. F is getting small, so g is getting big as it approaches the asymptote there. They cross at 1. And then same thing here. I'm going to take the reciprocal of the vertex, negative 4, which is negative 1/4. And go through. I'm not too, like, these aren't super accurate graphs. It is on a grid. We are plotting points. We are looking for some careful points. But in a lot of cases, we don't actually know where that point is of 1 and negative 1. We don't know those points. So I'm not too worried about that those are perfect, but your graphs should cross at 1 and negative 1. You should be careful to make sure they cross. But you don't need to come up with a whole bunch of other points or anything like that. Any questions? We're going to do one more. Remember graphing absolute value? So we are actually going to graph, this one just says graph f at x. But first I'm going to graph, let's say, g. And we're going to use transformations to graph this one. And absolute value is a fair bit like a parabola where you're kind of looking for the vertex. So we look at the shifts. And this one has a shift up of 3 and a shift right of 5. And the negative out front makes it do what? Flip, right? And then you might, I don't know if you think of it this way, but it kind of has the two arms of it have a slope of 1 and -1 kind of thing, right? So I just know from there that it's going down like this and like this. So that's G. Okay, and then just watch, this is what people do. So they know that they get the asymptotes because we do a lot of work with asymptotes, and most people are fine with the asymptotes. And then they do this. Looks about right? Like I thought, like, yeah, you followed that pattern that a lot of these graphs work out to, but that's not even close. That doesn't make any sense for this graph. They don't cross at 1 and -1, like they don't do any of the things that we talked about. But if you don't practice, that's what ends up happening. You just try to follow the vague recollection you have from class. So what are we actually going to do? We're going to make sure if this graph is negative, its reciprocal is negative, right? Like in the bottom part of the grid, below the x-axis. And it crosses at -1. So this one's going to go like this. And like this. And this one's going to have a point there at positive 1/3. Come down like that. Whoa. Like that. So it's essentially flipped, but if you don't do that thinking, like I said, as this graph gets really, really big, this graph, its reciprocal is going to get really small. As this one gets really small, this one's going to get really big. But both negative. Crossing at 1, and this graph again is getting really small here, so this one's getting really big. This one's getting really small here, so this one's getting really big. And this is 3 here, so this one's 1/3. You have to go through that thinking.